Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on November 13th, 2025, just yesterday. The main idea is a latent upscaler adapter that boosts resolution before decoding, delivering comparable image quality while cutting latency, adding only 0.42 seconds for 1024 pixel output from 512 pixels, compared to 1.87 seconds for pixel space super resolution with the same backbone. The paper is titled, One Small Step in Latent, One Giant Leap for Pixels, Fast Latent Upscale Adapter for Your Diffusion Models. And as we'll see later, the implications for fast high-resolution synthesis are quite significant. Figure 1 shows how the latent upscaler adapter lifts resolution earlier in the pipeline, so one decode produces a bigger, sharper image. It works on the latent code, a compressed internal image representation, which preserves semantics while cutting compute. The red path decodes the original low-resolution, latent to a standard output. The green path first enlarges the latent by a factor of 2, then decodes once, avoiding extra diffusion passes. The timing callout highlights practical speed, with the 1 kilopixel case adding about 0.4 seconds. Alright, figure 2 shows a head-to-head upscale to 2048 pixels that compares base decode, bicubic latent, SwinIR image super resolution, and the LUA latent method. The top row spotlights runtime overheads. The middle crops indicate that bicubic latent blurs and aliases, whereas SwinIR sharpens but drifts in texture, while LUA preserves eyelashes and crisp skin edges. The bottom Laplacian variance maps, which visualize residual noise by making darker regions mean less noise, reveal LUA with the lowest noise. For runtime, SwinIR adds about 8 seconds. LUA adds about 5 seconds. So figure 4 explains how the latent upscaler adapter routes latents through one shared brain and then picks a scale head, which makes the system fast and simple. The left blocks adapt to different VAE channel widths with a 1x1 convolution. The center backbone uses a SwinIR-style transformer that extracts features consistently across models. The right heads reconstruct higher resolution latents at 2 times or 4 times. Pixel shuffle here means the model rearranges channels into extra pixels, which yields crisp detail without extra diffusion. So Table 1 reports fidelity and latency across resolutions, giving a head-to-head view of methods. It shows the latent upscaler adapter is the fastest at 1 kilopixel. The direct decoding has stronger FID, where lower means the images look closer to real photos. At 2 kilopixel, it leads on speed and quality because operating in latent space avoids heavy pixel processing. The FID settles around 181. At 4 kilopixel, it remains fastest and posts the best patch fidelity, with PFID near 62. Alright, 2 takeaways stand out. First, upscaling the latent before a single decode delivers high-resolution images with near-native fidelity while cutting added time to well under a second at 1 kilopixel. Second, the shared backbone plus scale heads generalizes across different decoders with minimal tweaks. This paves the way for faster, cheaper, high-resolution diffusion in products and research. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.